next week I will be more organized.
So I've started the stream.
So are there people who expressed interest in doing something like this at such a time slot?
In doing what? Sorry. No,
is this
just
a response to some demand, or just...
No, it's just in response to the observation that for some people the time slot I had put was really obnoxious, so I thought it was not nice.
Yeah.
And it's not like a big constraint for me to just put 2 slots instead of 1.
Okay, and all the settings that are required for captions and things should be okay now. And I guess I'll start the live stream. I mean, not the live stream. The live stream is started. I'll start the recording. Spotlight JC.
All right, so maybe I can start, or no, maybe I should wait another minute.
Just
yeah,
maybe a minute.
All right, so maybe I should get started. So hi everyone, welcome back to this series of lectures on statistical mechanics of disordered systems. So as a reminder, last time we covered rather quickly this chapter 1 on large deviations and convex analysis. So I wanted you to have some sort of bird's eye view on what large deviations are, and also mention this result of convex analysis about taking the dual of a function and when it is that we recover this function. And we saw it happens whenever the function is convex and lower semi-continuous. So I put a lot of math into last time's lecture. I think today it will be more of the content will be more of background and historical comments about statistical mechanics in general and why we want to study statistical mechanics, how it comes to be. So, but overall, the chapter is on Curie-Weiss models, so a specific model of statistical mechanics. Before I go into this, are there specific questions on what we have done last time? So if not, I'm going to start with the first section on Gibbs measures. So Gibbs, I think his first name was Josiah, and he was a scientist, a theoretician working in the US near the end of the 19th century. And as far as I know, he's the guy who coined the term statistical mechanics. And now, yeah, we have this thing called Gibbs measure. So I'm going to explain some easy way to understand how Gibbs measures can arise, or at least some relatively simple context in which we can think that they arise. So suppose that we have we have n units, maybe particles. So we have so initially people were interested in studying matter. So you can think that each unit is an atom and maybe it has different states. So each unit, each unit can be in a number of states. Let's say k states. And we think of this number of states as being fixed, and the number of particles or units, this capital N, as being very, very large. Ultimately, I want to take n going to infinity, but k will remain fixed. Okay. And when a particle is in a given state, it has a certain energy. So each state, little k, has an associated energy. I will denote it Ek. And our system of n particles is isolated from the rest of the universe, or maybe it's the entire universe. And so the total energy of the system is conserved. Okay, it's fixed. And the total energy of the system is fixed. And I want to take it proportional to the number of units, so proportional to n. So say n times E bar for some fixed E bar. Okay. So E bar is some number which we fix, and I postulate that the total energy of the system is n E bar, and each unit can decide to occupy a state 1, 2, 3 up to k. And if it's in state 2, let's say, then its energy is E2. And then the same for each unit, and then the total energy is the sum of the energies of each unit. Okay. So, okay, so maybe I'm going to write it like this. When I sum the number of particles in state k, I'm going to write nk times the energy of the state. I want this to be equal to this big N times E bar. Okay, so where nk is the number of units in state k. So far, so good. And the question I want to ask is, so this is one constraint, but it does not fully specify the microscopic details of the model. We don't know by this prescription whether the first unit has energy E1 or E2 or E5. It's just this global constraint which is imposed. And from a physics perspective, I think it's Boltzmann who postulated that, in fact, the system will choose its state uniformly among all possible achievable configurations. At least this is what I'm going to postulate. Okay, so we have one constraint in the system. The sum of these nks, eks has to be a specific number. You know, this prescribes a subset of the space of all possible configurations. And I'm postulating that the system is distributed uniformly over this set. Okay, and like for this discussion, I'm ignoring, whether or not things lie on an integer. maybe if E bar is not properly set, maybe this relation is not possible, etc. So I'm ignoring this. So maybe you should think that when I write identities here, it's like up to a tiny approximation so that we don't have to worry about taking integer parts. Okay, so postulate that the system is uniformly distributed among all these configurations which satisfy the constraint. Okay, and the question I want to ask is, given that, what is the chance that a given unit, let's say the first unit, is in a particular state, let's say K? Okay, so in other words, I want to know, under this assumption, how does this number nk divided by n look like? And if you have thought about the second exercise of the first problem set, then it should ring a bell. It's kind of related. Okay, nk over n, you can think of this as the probability that a given unit is in state K. So so I'm going to rephrase a bit the question. I can ask, if I fix these numbers, n1 up to n capital K, how many configurations are there which are consistent with these numbers? So let's say number of configurations. Okay, so I'm going a bit. I'm not being very precise because it's just a motivating discussion I want to do here. But I'm thinking I'm fixing this list of numbers n1 up to nk. I'm asking how many microscopic choices I can do so that the number of particles in state 1 is n1, etc. And this is just the multinomial coefficient. We say n factorial divided by n1 factorial, etc., up to nk factorial. And now, it's like what we discussed at the beginning of last lecture. I want to understand the asymptotics of this when n becomes large, and all of these nks are proportional to n. So say nk over n is approximately fixed, equal to pk, just like we have done with this x last time. So I'm thinking that pk is essentially fixed, and n is going to infinity with this relation being preserved. And then I can do my Stillings approximation again on these factorial coefficients. So what happens, if you want, last time what we have done is the capital K equals 2. So log of n factorial is, we saw that it's about n log n minus n plus big O of log n. Okay, and then there are I should put minus, right? There are the other guys, so sum. And nk, I'm going to write pk times n. Okay, so pkn log pkn minus pkn. And then there is my error term, okay, plus O of log n. And yeah, I should have said earlier, but observe that this pk, it is such that the sum of the pk is equal to 1, okay? Because it's the proportion, pk is the proportion of particles in state k. So if I sum, I get, I get everything. So we see that there are cancellations, as we had seen yesterday. in this formula. So the n log n's disappear. The minus n and the minus pkn also disappear. And what remains is n times the sum of pk. So instead of writing, yeah, okay, maybe I should write minus. Okay, oh, okay. I like to write it like this because it's clear that it's not negative. Pk log of 1 over pk. The tilde over the single bar. I don't understand the question in the chat. Maybe it's because is there a typo? Oh yeah. Haha, sorry. Thanks. Someone understood the question. By this I mean it's essentially equal, but maybe because of integer, in taking the integer part considerations, maybe it's not exactly equal. So I mean equal up to a very small error. Yeah, thanks for this question. And thanks for the person who understood the question. Okay, and so this is our generalization of the quantity we had seen last time for k equals 2. And I'm going to call it S of P, the entropy of P. So this tells us, if I fix certain proportions of type 1, type 2, etc., it tells me that the total number of possible ways to realize this choice is approximately exponential of n times S of P, okay, for a fixed choice of P. So surely our system will because we take things uniformly at random, it will prefer those choices of P which maximize S of P. Okay, again, this is in the spirit of this first exercise of the first problem set, because if we have, let's say, 2 choices for P, just to make to discuss it easily, one will be exponentially larger in n than the other. So in the limit of large n, we will overwhelmingly only see the P's which maximize S of P. Okay, so the moral of this story is that the system will want to maximize S of P. It will choose the P that maximizes S of P. However, we have to remember that there is we have to still satisfy the constraint of the total energy being n times E bar. Okay, so our system maximize, let's say, to concentrate on these vectors P's that maximize S, but subject to the constraints that the so the total energy, okay, it's sum of nk, I'm rewriting it, equals n E bar, but nk, we said it's pk times n, so let me rewrite this as like this, so pk ek equals E bar, and of course there's also the constraint that the sum of the pk's is equal to 1. Okay, and the pk's are non-negative. Okay, so I was a bit quick, but I'm saying that, if you take, let's say, 2 competing P's satisfying the constraint, and one has larger S than the other, there will be exponentially many more configurations for the one with the larger S. So when we take something at random, and there's this huge collection of things next to something exponentially smaller, we will select only from the big bag, okay, from the guy which maximizes S of P. All right, so what does it mean? So what is this maximizer looking like? So I'm asking myself now, this is a simple optimization problem. I'm looking for the vector P, which maximizes S subject to the constraints that are written. And so I can apply the Lagrange multiplier theorem. And I know that the gradient of S at this optimizer has to be in the linear span of the gradient of these functional constraints. So the maximizer. Oh yeah, and I should have said, notice also that this function S of P is a convex function of P. Okay, so because X, let me get it. So yeah, so sorry, because I put 1 over, so it's a concave function. So it's minus X log X. This is a concave function. And so it's a concave function of the vector of PKs, which we optimize over a linear subspace, or in fact, maybe a convex subspace. So there will be a unique optimizer, and it is characterized by the fact that there exists. So P is such that there exists alpha and beta satisfying for every K so we want that the derivative of S with respect to PK is proportional to the derivative of this functional, so it's just alpha. Oh, I should erase this. Yeah, plus the derivative of some other multiplicative factor times the derivative of this other functional. So here I get some EK. Okay, so now we look into the function S and look at what this derivative is. So S is minus PK log PK. So when I differentiate, I will get minus log PK when I differentiate the PK. And then if I differentiate the log, I get minus 1. Okay, so minus 1 I can absorb into the alpha if I want. Okay, it's just a constant. And so what we find here is that PK should be proportional to, and I'm going to write 1 over Z for the, I'm going to call 1 over Z the proportionality constant. PK should be proportional to the exponential of minus beta EK. Okay, so this is what I wanted to arrive at. So if I summarize what has been done here, we take this isolated system with lots of units. Each of the units has K accessible states. And we say the system is going to choose uniformly at random over all accessible possible configurations. And we ask, what does a typical unit, in what state does a typical unit find itself if we let this n go to infinity? And the answer is we're going to find it according to this probability P, described such that PK is proportional to exponential minus beta EK. Okay, and that's what the Gibbs measure is I give you an energy function here, this E1 up to E capital K, and you construct, you give yourself some beta, and you construct the probability proportional to exponential minus beta EK. That's what the Gibbs measure is. And beta is called the inverse temperature. So this is what the Gibbs measure is. This is the Gibbs measure. Associated with this vector of energy. And beta is called the inverse temperature. And yeah, okay, so I should. It is prescribed. So, how do you find beta in this problem? It's prescribed by the requirement that the average energy is equal to E bar. Okay, so for each E bar, there will be one choice of beta. And okay, maybe it's not immediately intuitive that this is the inverse temperature, but at some point, if you want to answer the question, why is this a good notion of temperature, you have to ask yourself, what is the temperature? And in fact, when you do, let's say, the fundamentals of statistical mechanics, basically you define the temperature exactly in this way. So in fact, in my view, at least, this is how, at least this relates very closely to how the temperature is actually defined in the first place. And okay, so what is it want to say? Yeah, okay, so this I will skip. Okay, so maybe that's what I wanted to say on this. So perhaps another way to think about this is that, yeah, if I take a unit, so if I imagine that the universe is this huge collection of units, and perhaps I only want to study one particular unit among these many, and I ask myself, what distribution does it satisfy? It will be distributed according to this probability law, to this p case. I mean, yeah, maybe my comments about the definition of temperature was not very easy to follow, but I just mean that if you want to build statistical mechanics from the bottom up, you're going to start by some combinatorics, then you're going to introduce the entropy, then there is some notion of energy which is given by the specific system you look at, and then by definition the temperature will relate to how the entropy changes when you change the energy. So it's okay. Yeah, I don't know how to explain it better than this, but okay. So that was for the motivating explanation of what a Gibbs measure is. It arises naturally as when you look at a subsystem which is in contact with some huge thing that has a fixed energy, let's say. Okay, so that's one physical way to think about it. It's also useful to remember that I like to think about taking exponentials of things as we're going to compute Laplace transforms of certain quantities. So mathematically, it's also a convenient tool. It's not purely for physical reasons that I want to study what happens when we take our energy function and we look at the exponential of, let's say, beta times the energy. But okay, it also comes from this physics background. Okay, and yeah, I could. So from here, if you want, you can also derive. Yeah, so if you want to play a bit more with this formula, you can check, for instance, that the entropy, you can rewrite it as log of z plus beta E bar. Okay, it's a simple computation which I don't want to do, but and I don't know if you remember your thermodynamics classes back in the days, but so this is the so at least when I was exposed to this at school, I was told that so beta is the inverse temperature, and the formula was presented to me by multiplying by temperature. So I would have T times S equals the energy plus this guy called the free energy. So this guy up to multiplication by temperature is the free energy. So Z. So if I was really wanting to use accurate terminology, I should call it Helmholtz free entropy, I think, but I'm going to call it the free energy. Okay, and so I can write it explicitly. Z is the what makes it normalized, so it's the sum of the exponentials. Okay. All right, so that was a quick motivating discussion about what a Gibbs measure is. And now I want to, before I turn to the Curie-Weiss model, I will talk about a model which is actually more complicated, but it was historically introduced first, and it's the Ising model. Or at least it's my understanding that the Ising model was introduced first. Maybe I'm wrong. Okay, so maybe as again some bit of historical background. So around the year 1895, there was a Pierre Curie who was doing experiments in his lab with magnets. And he observed that he could impart magnetic properties to a material by submitting it to a magnetic field. So you take this piece of material, which now is called ferromagnetic. You put it in some magnetic field, and then you turn off the magnetic field, and the material will retain magnetization. It will still be a magnet. Okay, he observed that, and I mean that's we have magnets had been observed for a very long time. But what he observed, which was more striking, is that he could destroy this magnetization property by increasing the temperature. So he observed that if he raises the temperature, at some point, this capacity of the material to retain magnetization would disappear. And so then people call this paramagnetic behavior, when some material is not able to retain magnetization. And I don't think he came with an explanation. He just observed that this was happening. And there is this critical temperature that separates ferromagnetic to paramagnetic behavior, which now is called the Curie temperature. And then I think shortly afterwards, Pierre Weiss came up with some explanation of what at the time they called the magnetocaloric phenomenon. Magneto because there are magnetization involved, and caloric because temperature is involved also in the question. And okay, I'm not completely sure what he did exactly, but I suppose that he used, let's say, old-style thermodynamics to try to understand what was going on. And then, okay, some time passes, and in the 20s, Wilhelm Lenz proposes to his student Ernst Ising to study a theoretical model of a magnet. And the proposal is we place ourselves on ZD. Let me draw, I'm going to draw a two-dimensional piece, or maybe a finite subset of ZD, let's say a box. So let's say a box. And at each side, there is a +1 or a -1. So maybe here's +1, it's a -1, etc. And we think of each site, a +1 or -1 as encoding a microscopic magnet, which has two possible orientations, maybe upwards or downwards. And locally, these tiny magnets would like to rather be aligned rather than not, okay, because it feels it's energetically more favorable that the two neighboring magnets are going in the same direction. So Lenz suggested to his student Ising to think about this model in a more theoretical way. So let's say a Bn is the box of size n in dimension d. And the configuration in this problem is a vector of +1s and -1s indexed by the size of the box. And then the energy of the system, energy of the configuration, I'm going to call it Hn of sigma. I'm going to define it as the sum of sigma I, sigma j for I and j in the box, which are neighbors of one another. Okay, so this I twiddle j is to denote I is a neighbor of j in the nearest neighbor graph. Okay. And I should put a minus sign because it's more physically reasonable to. So this sigma I, sigma j is one if the two. So these macroscopic magnets are called spins. So if the two spins agree, this is one, and if they disagree, it's -1. So as I phrase the problem, the system would rather try to maximize Hn of sigma. Okay, but physicists prefer to minimize the energy. But I don't want to keep track of too many minus signs, so I will not put a minus sign in front. But most people will put a minus sign here. Okay, and now okay, this is the energy function. So clearly, it's most favorable that if we want to just maximize this energy function, we're just going to put all the sigmas to be +1 so that everybody agrees, or all the sigmas to be -1 so that also everybody agrees. But in real life, when we have our magnet, it's not really managing to find this optimal configuration because there's a lot of thermal noise. And so instead of saying that the system is trying to optimize its energy, we should follow the prescription of Gibbs that I described, which is to say, to postulate that the system will, in fact, distribute itself according to the Gibbs measure associated with this energy. So at inverse temperature beta, we find the system in configuration sigma with probability proportional to the exponential of exponential of beta times the energy. So proportional to, I'm going to actually write with probability. I'm still going to call Z the normalization factor, but now it depends on n, and on beta, and then exponential of beta Hn of sigma. Okay, and Zn is so that the sum of the probabilities is equal to 1. Okay, and perhaps if we want to be more faithful to, if we really want to mimic this experiment of Curie where he was submitting these pieces of material to an external magnetic field, I should also add a term that encodes this external push in a direction. So let me add this. So with external field, which I'm going to encode by a parameter h. So now the probability depends on beta and h. So I'm going to write Zn of beta and h, and then exponential of beta HN of sigma plus this extra push. So all of I'm adding this term to the energy function. Oh, sorry, not this. So I in the end. Okay, so if H is positive, I give an extra energetic reward to having sigma being +1. So H is pushing the spins in the direction of the sign of H. And of course, the larger H, the more the push is significant. Is it clear what probability measure I'm talking about? So it's a probability measure which gives the probability as displayed here to a configuration sigma, where Zn is so that when we sum over all possible sigmas, we get 1. So perhaps you would object that this should be part of the energy function. And so really I should put the beta like this, because we said it's beta times the energy function. And you would be right. But mathematically, it's more convenient to be allowed to play separately with beta and H. So I'm not going to put parentheses like this. Okay. We are, after all, we are going to do mathematics. So we have to make our life as convenient as possible from a mathematical point of view. Okay, so it's best to define it like this. So the point of the sigma j is that what I want to say is I want to make sure what I want is to say that the two neighboring spins should agree with each other. Yeah, I don't say I want them to go up or I want them to go down. I just want to say they have to agree with each other. Okay, so once we have defined this probability, we can try to compute the resulting magnetization in the system. So which is so the resulting magnetization is maybe the mean of these sigma i's under this measure. So let me write this. So the resulting, the induced, maybe I could say. I'm going to denote it M sub capital N. And so it depends on beta and H. Okay, I'm just going to write some more sigma. Okay, and I'm not rewriting, but it's the same. This dot 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 is the same as what is in this exponential. Okay, so what I'm doing here is that I'm looking at this object, sum of sigma I divided by the number of sites in the. Yeah, this is just the mean magnetization. So this is the mean magnetization taken with respect to this probability measure. Okay, and I want to see if in my model the observations of Mr. Curie are showing up as well. Okay, so as a first pass, maybe I can just try to plot how this object behaves, and I just take n to be very large. Okay, and so what happens is that for small beta, the curve looks like this. So it's really the most reasonable thing you can imagine, because, well, by symmetry, this magnetization will be an odd function. And if you really insist on putting H extremely large, you will force the spins to be +1. So to H plus infinity, it will go to 1. And in the middle, it will be 0. And then it's odd. So it will have the shape will be sort of like this. Oops. Okay. It goes through 0 here. And then the limit to the left and the right is -1 and 1. So it stabilizes like this when we, so this is H, and the curve is the resulting magnetization for n very large. But for large beta, what we observe instead is that there is a discontinuity near at 0. So it's still, when h goes to infinity, it still goes to 1, and in the other direction, it goes to -1. But there seems to be a jump. Yes. There seems to be a jump at the origin. At least, when we take n very large, for any fixed n, the function is continuous in h. But when n becomes large, it seems to be really extremely steep. And in fact, we can show that. Okay, so yeah, so just to stick with the history of the problem, in fact, Ising focused on the case in dimension 1, and in dimension 1, he showed that for any beta, even in the limit, this curve is actually continuous. There is no jump, as I kind of try to picture here. And if you do exercise 1 of the second problem set, then it's a derivation of this fact that this object is actually continuous even after you pass to the limit. And then nothing much happened until around 1936, when Rudolf Peierls showed that, in fact, in dimensions 2 and larger, indeed, there is a discontinuity in this curve when beta is sufficiently large. So this is discontinuous for d larger than or equal to 2. So because I could not resist trying to outline the argument of Peierls to show that indeed there is a discontinuity here. So I also put it in the second problem set, but it's somewhat tangential to the main point of these lectures. So if you have time to think about it, I think it's really a very nice piece of mathematics. But like if you are overwhelmed by the amount of problems you have to do, don't worry. Okay, so yeah, maybe I can take a short break. So let's say 10 minutes or maybe somewhere between 5 and 10 minutes of pause now. Yeah, sorry, good question. What is interpretation? So this matches, I think, the experiments of Pierre Curie, because you see that if you take your system and you apply a tiny bit of H positive to your system, it will in fact spontaneously organize itself into something which has a lot more pluses than minuses. Okay, so just because you give it a little bit of a suggestion to go towards the plus, it will spontaneously align itself in the plus direction. Okay, because the neighbors, they want to be aligned with one another. So in principle, I should have explained this more. Thanks for the question. In principle, your system is really trying to make sure that two neighboring spins agree with each other. So if you take this literally, then you will have to align all the spins. But in fact, because there is this extra disorder thing, it's not always happening, and it depends on beta and depends on dimension. Let me display again the measure. So yeah, someone in the chat asked, so the dot 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 is really what is here. So you see in this sum that is here, there is a competition between trying to optimize what is in the exponential And the best thing you can do in the exponential is setting all the sigmas to be +1. Let's say h is positive. This is what maximizes what is inside the exponential. And if this was the dominant term in the sum, then this term will be 1, and what you would see as the mn would be just a +1. But this is not the entirety of the story, because maybe the other configurations, they get a smaller term in the exponential, but there are much more of them. So even though they are kind of not performing so well in terms of the value of this exponential, they are so numerous that in fact these are the guys which dominate the sum. Just to make things clearer, imagine beta is equal to 0, and let's say also h is equal to, maybe h is only extremely tiny, so you have only a tiny bit of incentive to be positive. Then this magnetization will be very, very small. The h will have extremely little effect on this quantity. And as you increase beta, this competition between the weak guys, which are numerous, and the strong guys, which are fewer, turns in the favor of the guys which are fewer but more powerful in the exponential. Does that make sense? Cool. Yes. So I see, maybe I was not very clear with this alpha and beta. So what I wanted, so let me go back to what I'm trying to do here. I'm saying that the set of P's that we care about, they have to satisfy the constraints, which are those two constraints. For this total energy to be preserved, I have to satisfy this. And also the sum of the fractions have to be 1. And also, okay, they are non-negative, but this will work itself out, so let's not worry about this. But so this, if I want the configuration to be allowed, I have to satisfy these constraints. But now among the allowed configurations, those that will dominate my measure will be those which are more numerous. And this question of cardinality is driven by the number S of P. So among those configurations, we should maximize S of P. Okay, so the problem I'm trying to solve is, what is the maximizer of S given the constraints that are in the squares? Okay, and the reason, like, this is, if I fix the P's, the number of configurations is given by this number, okay, except you replace nk by pk times n. And this number, we said it's, okay, if I take the log, then basically it's n times S of P. Okay, so if I don't take the log, it's exponential of n S of P. Okay, so let me go back to my program then. Yeah, so I'm trying to optimize S subject to these constraints. And then by Lagrange multipliers, the optimizer has to be such that this property holds. Okay, there exists alpha and beta such that for every k, this is true by Lagrange multipliers. And then, okay, then the rest of the derivation follows. Is it clear? And yeah, it's like, when yes, so I'll add one more comment and then I answer to this question in the chat. So when I was trying to explain this competition between this term in the exponential, which is the energy, and the fact that maybe some other terms are more numerous, you can see it already in this formula. This is the energy, and this is the entropy, which counts the number of configurations of a certain type. So here, this is a representation of the free energy as a combination of entropy and energy terms. Well, that's just a side comment, but okay, let me not continue this direction. So to come back to the question in the chat, you see, when n is fixed, this is a totally reasonable function of all the parameters. It's infinitely differentiable in all the parameters, right? Because we're only doing I take age, I put in the exponential, I sum a finite number of terms, I do nothing hairy. So this function is smooth in the parameters as long as n remains finite. So the discontinuity only shows up after I pass to the limit. So I'm trying to, so for small beta, indeed, what happens is that it's the force of the numbers. The fact that the configurations with small magnetization are much more numerous is what overwhelms the sum. So the guys which have a better energy term, energy term is what is here, they are not numerous enough to compensate. So that's what happens for small beta. And for large beta, it's the other way around. Like the numerous guys, they don't win out, and the exceptional guys dominate. Okay, so how do we justify that we use the Gibbs measure in this context? Because when Curie does his experiments in the lab, in fact, the magnet is not in isolation with respect to the universe. It has a given temperature, which is prescribed by the fact that it's in the lab and stuff, and so it's going to be bombarded by exterior things. It will have some internal disorder provoked by the thermal fluctuations, and so it's the way it's going to settle down is prescribed by the fact that its temperature is fixed in the lab. And this temperature is this beta parameter. Yes. Right. Okay. Okay. So maybe that's so yes, indeed, the discontinuity only happens after we pass the limit. All right. Thanks a lot for the questions. That's really nice for me to get feedback, because it's much easier for me to gauge if you're with me or not if you ask questions. Otherwise, I just don't. All right. So I want to, these were drawings that maybe nowadays we can do on our computers, but now how can we do mathematics concerning this quantity, especially when it comes to understanding the the limit behavior? We have to resort to more theoretical arguments. So instead of trying to focus on this quantity directly, I want to focus on what from now on I'm going to call the free energy. So it's the log of this z parameter. So let me write this. So let's study or consider the free energy. I'm going to denote it Fn of beta and h. So it's I'm going to normalize by 1 over n. Okay, or 1 over the volume, sorry. So if I rewrite Cn of beta explicitly, it's this normalization constant. So it's the sum of the exponentials over all possible configurations. This is the sigma. Okay, so maybe at first sight you think it's kind of bizarre to study this quantity. So hopefully I'm going to answer this question. Yes. So why do we want to study this quantity? Like it's kind of, at least at first sight, maybe now I said already so many times that I think of this as a Laplace transform, that it's less surprising. But initially you may think, but this is the normalization constant in the probability measure. Why do we care about the normalization constant? What we want to understand is the probability measure, not the normalization constant. But the point is that, yeah, indeed, I think it's best to think of this as a Laplace transform or moment generating function of the variables we care about. And in particular, here I can display rather clearly why this object is interesting. Because if I differentiate in H, what will pop out is precisely this mean magnetization Mn. So let me do this calculation. So observe that when I differentiate in H, this quantity, well, okay, that's still the 1 over this normalization I've put there. And then when I differentiate the log, I get the derivative divided by the object itself. And the derivative, so let me try to do this computation in one shot. So when I compute the derivative of this thing here, this sum over sigmas, what will happen is that maybe I should use this. This term here will be brought back in front of the exponential, right? That's what happens when we differentiate with respect to H. I'm going to write it. I don't know why I didn't want to write it. So it's sum over sigma, oops. And then sum over I of sigma I times the exponential of blah, blah, blah. Okay, same thing. Dot, dot, dot is this beta Hn plus H sum of sigma I divided by sum over sigma of exponential of the same thing again. Okay. And we recognize the mean magnetization here. Okay, so let me display it one more time. So I'm going to scroll back up to display the mean magnetization. It's here. So we have sum over sigma of sum over sigma I exponential of blah, 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 divided by this Zn, which is the sum of the exponentials. Okay, so this is exactly Mn of beta H. This is equal and the point is that if you have two, if you care about the derivatives of a function, it's going to be easier for us to try to understand the convergence of the function itself versus trying to directly confront with the convergence of the derivatives. Okay, so the function itself will be more robust to small modifications of the model, for instance, or so it will be easier for us to have access to Fn and then deduce later information about its derivatives rather than try to directly confront the derivatives. Does that make sense? So even though maybe in truth, what I really care about is understanding this Mn function, I'm going to first concentrate on studying the function Fn. And then at a later stage, I'm going to wonder whether the derivatives of fn converge to the derivatives of the function itself. And in fact, it's not very difficult to show that this function does converge. To some limits. And moreover, indeed, so it's not difficult to show that it converges, but identifying what is the limit, this is a more difficult question. Because in the MN guy, there is 1 over Z, if you remember. So there's a question in the chat about what happens to, sorry, I'm flipping back and forth. There's a question in the chat about what happens to this guy, as far as I understand. And this thing is the 1 over Z in the previous formula. Yeah, and moreover, so this I'm going to explain later, but for now, I just take it for granted. The thing is, wherever f is differentiable, indeed the derivatives of fn converge to those of f. So one can show, oops. That the derivatives of fn converge to those of f wherever f is differentiable. And this is based on the fact that these functions are convex differentiable. So in this context, you use a subadditivity type of argument. You look at fn on the big box and you try to compare with systems in smaller boxes, and you try to show that this forms a Cauchy sequence. But okay, yeah, I'm not going to go too much into this, but it's possible. And also for those who know already a bit about the Ising model, you could make it so that you impose some bizarre, like some specific boundary conditions at the boundary of the domain. Like maybe you could imagine that these spins are in contact with those outside of the box, and those spins outside of the box have a fixed orientation, maybe +1, maybe -1. And one way to kind of observe that this function fn is nice is that the limit that you get does not depend on these boundary conditions. So it's a very stable quantity in some sense. And the derivative thing is with respect to any derivatives. So if you look carefully at this function fn, it's a jointly convex in both variables. And using this, you can show that wherever f is differentiable in H, the derivatives in H converge to the derivative in H. And wherever it's differentiable in beta, the derivative in beta of fn converges to the derivative in beta of f. Okay, so all this to say that if we could, instead of just saying, this limit exists, if we could put our hands on what this limit is, that would be really great, because we would completely be able to answer these observations of that I just did earlier, with the graphs, with the discontinuity or without discontinuity. Okay, because what this predicts is that at the level of the function fn, it will be at least C1 when beta is small, and then when beta is large, the plot I gave is in fact the plot of the derivative. So it means that the function is having a corner at the origin. The derivative when you approach to the left is negative and stays away from 0. And then when you approach to the right, it's positive and it stays away from 0. So it has a corner at the origin. So in some sense, if we could identify this limit and observe that it has these properties, then we would be able to assert rigorously that these pictures I drew of these graphs is actually valid. So it's not an easy task. So in the second problem set, the first exercise allows us in fact to compute this limit explicitly. So we say fn converges to the limit f, and here it is, and we display it. But in higher dimension, it's in general a bit of a hopeless task to compute explicitly, to give a formula for what is the limit. And this is just a historical comment, but I think it's a very important thing to have in mind. What really made the Ising model so important in the history of statistical mechanics is that at some time, I think in the late 40s, Onsager observed that he can in fact compute exactly the limit free energy of a two-dimensional model. Okay, Onsager and I think Schäger and Young also contributed to this. So that was a striking achievement, which is obtained by some rather ambitious generalization of the argument that is used in the one-dimensional case. So if you solve this one-dimensional case, you will have a glimpse of how it works also in the two-dimensional case. And it really struck people because Onsager, using these exact computations, could not only verify that this jump occurs, because this was already known to Pyers, but he could also understand precisely what happens at the transition. When you switch from ferromagnetic to paramagnetic behavior. So Onsager computes this f for d equals 2. And in particular, so he showed that indeed, so there is a critical temperature at which the discontinuity is about to emerge. And at this critical temperature, the curve starts to look very singular near the origin, and he could show that. So this is the picture in H of this mean magnetization. So normally it's a smooth thing, but when you are at the critical point, just before the emergence of this jump discontinuity, he showed that the behavior of the function here is like h to the power of 1/15. And I think before that, nobody had any clue that 1/15 would appear in this problem. And similarly, so let's say for beta larger than beta c, but close to beta c, then once the discontinuity emerges, so this is just a little bit above beta c. He showed that this gap that starts to emerge behaves like beta minus beta c to the power of 1/8. So this is when beta goes to beta c from above. And this also was really completely unexpected. And so later we study Curie-Weiss. I'm going to explain what Curie-Weiss is. And these exponents are different for Curie-Weiss. So that really struck people, and that also told people that, first of all, there were lots of things they did not understand about critical phenomena, and second, that in fact, it was not a hopeless task. For this model, we could actually say something about critical phenomena. And because of these two related aspects of, you don't understand, and actually there are things to be done there, this triggered an enormous amount of activity in a sequel. Like, statistical mechanics became a very active topic as a result. Okay, so I think the main message I wanted to convey with this discussion about the easing model, well, first, I think it's interesting to have some background about where statistical mechanics come from. And second, I think it's also the takeaway messages I want that you take from this is that first there is this quantity called the free energy, and it looks a bit innocent perhaps at the beginning because it's just the log of this normalization constant, but in fact it's a very convenient tool to study because if we understand it, then later we can recover useful information about the system we care about by taking derivatives, basically. When we compute derivatives, we compute mean values with respect to the Gibbs measure. And the second thing is, so it's therefore very attractive to try to compute the free energy, and it's not always possible. We don't know how to do it for the easing model in dimension 3, for instance, or in any other dimension. But if we can do it, then we should try our best to do it. All right, and so are there questions? Maybe I should. So I don't quite understand the question in the chat. Not that I know of. Or yeah, so I don't see connections with the two topics mentioned in the chat. So if this made sort of sense, I want to start to introduce now the Curie-Weiss model per se, which is the model I really want to focus on for a long time. So I think it's the third part. So I don't know if maybe some people will know more about this than me, but as far as I understand, the Curie-Weiss model was introduced actually kind of later, maybe around the 50s. So at least, I did not go very deep into the papers of Weiss, but I'm not sure if he actually introduced the model as we know it now. Okay, anyway, so maybe just to summarize before I define the Curie-Weiss model. So there are two useful properties of the easing model that we like to use when we study it. One is a property I alluded to when someone asked me, how do you show convergence of the free energy? Is that you can make box decompositions. You can say, okay, I'm studying this problem in a big box. I'm going to think it's just a collection of these sub boxes, and maybe if I understand, if I can compare what happens in a small box to what happens in a large box, I'm going to learn something about my system. So that's one property which is useful. And the other property is that it has a motonicity property. So let's say that H is positive, then if I take a spin and I put it to +1, this will increase the probability that the other spins are also in +1. Well, it doesn't depend on the H, actually. It's always the case that when you take a spin and force it to be +1, you're increasing the probability that the other spins are also +1. Okay, and this motonicity property is very useful when we study the model. And these two properties will be destroyed when we look at these spin glass models like the SK model I discussed in the first lecture. But for now, I don't want to destroy both at the same time. I want to keep, I don't want to add randomness into the problem. I just want to simplify the geometry. So the easing model, it's defined on this grid. And instead of the grid, we're going to assume that all the units interact with all the other units. Okay, no geometry, or if you want, the geometry of the complete graph. So this will actually destroy the possibility to do decomposition into boxes because there is no really box. And if you try to, when everybody interacts with everybody else, if you try to make subsystems of size, half of the total size, then you cannot really neglect boundary contributions. So when you're on RD, if you decompose RD into let's say a box in dimension 2 into 4 subboxes, the boundary becomes negligible as n becomes very large. But when we're on this complete graph type of interactions, when everybody interacts with everybody else, it is no longer quite possible to split into two problems and say that boundary interactions are kind of negligible in the limit. So we will lose this this feature. On the other hand, because we simplified the geometry so much, surely we will gain a lot in terms of like the difficulty of the problem will reduce significantly because the geometry becomes so simple. Maybe another way to think about it is that when you do this model in the Ising model in the box, there are very few, the group of symmetries is relatively small. When you do this model where everybody interacts with everybody else, all of the permutations leave the model invariant. Okay, so you have a huge group of symmetries, and this should help us in some way. All right, so let me define the model, and then we will resume from there next time. So the Curie-Weiss model. We trivialize the geometry by making every spin interact with every other spin. So the energy function now, so maybe I should say first the configuration. So now there's no point to keeping this indexation by vertices in the box. Okay, so I'm just going to think of the configurations as being a vector of +1s and -1s of length n. And the energy of the configuration sigma, I'm going to stick with the notation Hn of sigma. I'm going to, so now I'm going to put the parameter, so instead of beta, I'm going to write t, and you will, because I already alluded to the fact that at some point there will be partial differential equations, kind of nice to have a t at this place. So I'm going to call t where I use beta so far. Okay, so t in some relatively unfortunate circumstance, t, you should think of it as being the inverse temperature. Okay, so little t, it's the inverse temperature. So t over n times sum of sigma I, sigma j. So now it's sum over all I and j. Okay, so there are n square terms in this sum. And because I want to keep my energy being over the n, and here there are no stochastic cancellations. Okay, so this has potentially will be over the n square. I divide by n so that it stays over, in total it stays over the n. T is a parameter, it's a parameter that is the inverse temperature. So for T positive and H positive, and then I'm going to keep this magnetization guy. sigma. Yes. So it's true that when I sum over all the, so there's a question in the chat about my including the case I equal j in the sum, and that may look a bit strange, but this term does not depend on sigma. And when you build this Gibbs measure, I'm just prescribing that the probability should be proportional to exponential of hn of sigma. So if I change hn of sigma by constant, it will just multiply all these exponentials by a constant. And so in fact, it will not matter as far as the probability is concerned. Okay, because in any case, we have to normalize the measure. Yes, does it make sense? Like we're saying it should be, the probability measure should be proportional to exponential hn of sigma. I'm going to rewrite it later, but just to clarify this conversation. So if I add a constant to this, if I say, if instead of telling you, oh, it should be proportional to exponential of hn of sigma, I tell you, oh, it should be proportional to 2 times exponential of hn of sigma, nothing has changed, right? I'm saying the same thing. So that's what I mean. So here, yeah, I find it slightly more convenient to put this beta parameter inside the definition of H now. So sorry about this. So just to clarify the definition, so there is the energy, and now the free energy, it should be the normalization constant inside to make it be a probability measure. So Fn, I'm going to call it Fn of T and H. And okay, I normalize by 1/n log of this sum of exponentials. Yeah, so maybe I should let me give it more precise notation. So this is Hn of T, H, and sigma. Okay, because maybe it's a better notation. Okay, so oh yeah, thanks for this question. No, this is not relevant. Let me erase this. Thank you for this remark. So H is just a real number. Yeah, I want to keep T non-negative because T is the inverse temperature. We want to keep temperature non-negative. But H is any real number. Thanks a lot for this question. And okay, so I'm going to add a 1/2 to the n here, so that it looks more like a probability measure, this thing here. Okay, this now is a probability measure. But you see, in terms of, this just changes the function Fn by a constant. You can pull out log 2 here, or minus log 2. And so in terms of computing derivatives of this function, this does not matter. It's just to make things match more nicely with the large deviations conversation we had earlier. So I'm going to define the free energy like this. And now the associated probability measure, I'm going to introduce a notation for this. So I don't want to write all the time a sum of sigma of exponential blah blah blah. When each time I want to compute some expectation with respect to the Gibbs measure. So I'm going to use the following notation. So this angular bracket of f of sigma. So this, you should think of this as it's an expectation, and sigma is the random variable in this expectation. Okay. And by definition, this is so it's the sum over sigma of f of sigma exponential of hn th sigma divided by the sum of over sigma of exponential of hn th sigma. Okay, so this is my Gibbs measure. Does it make sense? Is the definition clear? So for this model, I want to ask the same questions I discussed informally for the Ising model. Namely, can we understand this mean magnetization? For if I plot the curve, does it have a jump in the same way? Let me display these curves again. Does it look like the curves with the jumps were further above? Perhaps if there is such a jump, then maybe we can ask more refined questions like, can we identify? Oops, that's not what I meant to do. Can we identify the exponent here or the exponent there? Are they the same as for the Ising model or not? And yeah, intuitively, it should be easier to answer these questions for this model because, as I said, the geometry is much simpler. Okay, so just to make sure we connect the notations, different notations I used today, this mean magnetization, now I can write it just like this. So it's so here the number of spins is n. And this notation is, okay, if I was being more precise about this notation, I should keep in mind that it depends on t and h, right? But it's convenient to not write t comma h everywhere, so I don't. But this is the object I want to study. And as before, we can plot it as h varies and ask if it has a jump discontinuity when what was called beta, which is now called t, is small, or when t is large. Does that make sense? So I think it's about time to stop. So thanks a lot for your attention. And yeah, next time we are going to apply large deviations to understand this Curie-Weiss model precisely. I don't remember exactly. So there's a question about these exponents, 1 over 15 and 1 over 8. Surely they are believed to be valid for other two-dimensional graphs, but I don't know how much has been proved. But if you change the dimension, the exponents will change. In dimension 3, the exponents are not known, and there is no conjecture for what the exponents are. At least I'm not aware of any conjecture. And in fact, in dimension 4 and higher, the exponents are the same as for Curie-Weiss. So I did not say what they are, but they are different, and they are the same as for Curie-Weiss. And it's proved at least in large dimension or for some modifications of the model. Yeah, so if you haven't done exercise, so in terms of what you can do, if you haven't done exercise 2 of the first problem set, I think it's worth having a look. Maybe not necessarily justify everything, but at least understand how it relates to the thing I discussed today. And then you can try to compute the limit free energy of the Ising model in dimension 1. This is the first problem, the first exercise of the second problem set. And yeah, there's a great question about, is there a connection between high dimensional Ising on the lattice, like a high dimensional lattice Ising model and the Curie-Weiss model? And the answer is yes. And the reason is in very high dimension, the yeah, okay, it's not super easy to explain, but in some sense, the loops of the graph become less significant. In some sense, maybe it's not the best way to explain it. Maybe I should just say that in some sense, the Curie-Weiss model is when the dimension is n and you let it grow with the system. So maybe it's plausible that there is a connection between very high dimensional easing and Curie-Weiss. Maybe you could think as a first pass to let the dimension go to infinity with n even, and maybe Curie-Weiss is doing something like this. And indeed, it has been proved rigorously that the exponents that show up here, so instead of 1/15 and 1/8, different exponents show up for Curie-Weiss. And maybe I won't reveal what they are because it's one of the questions in the problem set, but maybe next time I can say what they are. So yeah, if you have time, you can also try to confront. Okay, this is a bit early. No, so okay, sorry, I'm going ahead of myself. So okay, for the Curie-Weiss model, okay, let me just look up what the exponents are to make sure.